Okay, it is an honor for me to introduce José Seade. I guess most of you know him very well. He's a very distinguished Mexican mathematician. And as Ilyashenko mentioned last week, he is one of the people thanks whom the important collaboration with Russia began. So it's a pleasure to have him here. And today he will speak about on the connectivity of the singular set of holomorphic foliation. Please,
Okay.
go ahead.
Thank you. Muchas gracias. Es un gran honor para mí estar aquí. And it's a great honor to be in front of Professor Ilyashenko. Thank you. And thank you all. Thank you, Laura, for the invitation. Thank you, the organizers. So I'm going to speak about, it's a new article that is just finished, which I've been doing with Omegar Calvo from CIMAT, Mauricio Correa, Brazilian in Italy, and Marco Jardim. So this involves many things, so I will speak more. It will be an introduction to complex geometry somehow, some aspects of complex geometry. So let me start by saying that in his paper, some problems on foliated geometry for the 60 years of IMPA, Dominique Servaux asked, if you have a codimension 1 holomorphic foliation on P3, and you look at the singular set, which is a union of one-dimensional irreducible components, and perhaps lower isolated points. You look at the one-dimensional set, and the question is this necessarily connected? And it actually is a very deep question, because, for example, in P3, there are examples, known examples of, I will speak more, but having a foliation means, you can think of it in many ways. One way is you have a distribution by two-dimensional planes, holomorphic distribution by two-dimensional planes. That's the first step. And then this distribution is what is called integrable. And then that's a foliation. And there are examples of holomorphic foliations in P3 with a one-dimensional singular set which has several connected components. Okay? So if we put this question at the level of holomorphic distributions, it's false. However, we'll prove that it is true. In fact, we'll prove something more general. We prove the following theorem. Suppose you have a compact complex manifold any dimension and a singular holomorphic foliation any dimension, less than n, and more than 1. For vector fields, for one-dimensional is false. And then look at the determinant bundle of the foliation and assume it is ample, which is always the case if you consider a foliation in Pn. Look at the singular set, assume it has some components of dimension k minus 1 and possibly something of lower dimension. Look at the k minus 1 dimensional set, and then that's a connected set. That's the theorem. Okay, so the previous question is a especially interesting case. Now, the proof, let me give an outline, a very, very quick outline, and then I will start explaining the things slowly. Well, so before the outline, let me say that we use very much what is called the Baud-Bond residues. They were mentioned in the previous talk. Well, Raoul Bott in the 60s demonstrated, he proved that certain topological restrictions, topological constraints, can obstruct the existence of integrability of a distribution. Okay? And so our theorem goes a little in that spirit. And we use very, very strongly what came out from that, which is the Baum-Bott theory. And so we use the Baum-Bott residues. Let me say a few words about this. And then let me start by recalling something that you all know. A k-dimensional singular holomorphic foliation on a compact complex manifold means that you can think of it as you have a short exact sequence where this is what we call the tangent bundle, tangent sheaf. This is the tangent bundle, thinking of it as the sheaf of holomorphic vector fields on X. This is what we call the normal sheaf. And F is integrable and coherent, and the normal sheaf is coherent and torsion-free. And by definition, the singular set is the set of points where this is not locally free. Okay? That's the singular set of the foliation. And, well, the rank of this is the codimension of the foliation. And this is actually a vector bundle away from the singular set. Well, and something important is that over the singular set, this is not, in general, a vector bundle. However, if we look at its determinant sheaf, that's always has, it's a one-dimensional, the rank is one-dimensional, and that's always a vector bundle. It's always locally free at the point, at the singular set. So it's a bundle. Then we speak of the normal, determinant normal bundle, and in the sequel, we'll ask it to be ample. Now it doesn't matter. Okay. I hope you like the talk. Uh-oh. My goodness. Is that it? Yes, I think that's it. Okay, so the genesis of the bound-Bott residues is Bott's vanishing theorem. I will say a little bit because if not, it's hard to understand what the residues are. Then the theorem is very beautiful, very easy to state. So you have a compact complex manifold and a non-singular, for the moment, non-singular holomorphic foliation of some dimension k. Then you look at the normal, in this case you have the normal bundle. The normal bundle is of dimension n minus k. So you have chain classes C1 up to Cn minus k. Chain classes of the normal bundle. Okay? And then what the theorem says is that if you look at any cohomology class of dimension greater than the codimension, and if that cohomology class is a polynomial in these classes, then it vanishes. Okay? And one, at first I could say, so what? This is very interesting. Yes, it is very, very deep. So let me just give a toy example, just to show its power. Just recall, we all know that you have a manifold, smooth, not even complex, with zero Euler characteristic, then it admits a continuous or a smooth vector field with no singularities. If it's a complex manifold, it has a vector field with no singularities, and that implies that the Euler characteristic is zero, and that's the same as saying that the top dimensional chain class vanishes. Okay? But now suppose the complex manifold actually admits a nowhere vanishing holomorphic vector field, not continuous. Suppose it admits a holomorphic vector field. Then all its chain numbers vanish. The chain numbers are all products of the manifold, all products of the chain classes of the manifold of top dimension, evaluated on the orientation cycle. Okay? So if it admits a holomorphic vector field, all chain numbers vanish. If it admits a smooth vector field, we only know that the top chain class vanishes. So that shows how powerful this theorem is. So the next question Bott and Baum addressed was, well, the next question is what about singularities? But just let me say a few words before coming to singularities, because I think I love this theory. I think it's very, very, very powerful, very interesting. And just let me give an idea of the proof. So chain classes, I'm a topologist, so for me they are obstructions for constructing sections of a fiber bundle, of a vector bundle. But for a differential geometry, they construct them using chain veil theory, using a connection. If you have a connection on a vector bundle, you have associated the curvature tensor, and with that, you construct chain classes. Okay? And then What notices that when you have a foliation, a non-singular foliation, then you can define something that he calls what is a connection? A connection means on a vector bundle means that you can look at the sections, and whenever you have a vector field, you can differentiate the sections with respect to the vector field. Okay, this is like a derivative, it's like a derivation of the sections of the bundle. Okay, then Bott realizes that when you have a foliation, the foliation gives you an action on the sections of the normal bundle. And that action is actually flat, which means that the curvature is 0. Sorry. Well, yes, that's correct. And then he extends, but that's only for when you consider derivations along with vector fields tangent to the leaves, not in all directions. Only when you consider derivations along the leaves, you have this connection that he calls partial connection, because it's only defined in that direction. But then he shows that this extends to a global connection, which is flat in the direction of the leaves. Okay? So that implies the vanishing of some cohomology classes of top degree, of high degree. And that's the idea of why all the combinations of Chern numbers of the normal bundle above the codimension vanish, because you have this flat partial connection. Okay, so now what if you have singularities? Well, then they think, okay, outside the singular set, you have this partial connection. So this should allow us to localize our Chern classes, our combinations of Chern classes there. Let me illustrate this with something that you all know pretty well. We all know the Poincaré-Hopf theorem. Okay? What does it say? Suppose you are in a complex manifold. It tells you if you have a continuous smooth vector field with isolated singularities, the Euler characteristic is the sum of the local indices. Okay? We all know that. But let us look at it from this viewpoint. Okay? So the Euler characteristic, let me think of it as being the top dimensional Chern class of the manifold. That's Gauss-Bonnet, so to say. Okay, so yeah, here it is. Suppose you have a compact complex manifold of dimension n, and almost complex could be enough for what follows. That means a complex structure in the tangent bundle. But suppose, and you have a continuous vector field with some singular set, S, all we need from it is that it be compact. It doesn't need isolated points. Suppose you have a compact singular set, and look at the connected components. Okay? And now for each take a regular neighborhood so that they are pairwise disjoint. Okay, so you have the manifold. And let me look, this is one connected component. We have many, maybe many, that's one. So we look at a tubular neighborhood, regular neighborhood of it. Okay? Away from S, we have the vector field with no singularities. Okay? Then you can look, well, now let me think as a topologist, and the top Chern class is the obstruction for constructing a non-zero vector field. Okay? Well, since the vector field here, away from S, is non-zero, and let me do it for all components of the singular set. Let me call U the union of all these tubular neighborhoods. Union. Okay? R. Then, when you look at X minus U, the vector field is non-zero everywhere. Okay? So that. Yes, I will. Okay, so if you, away from these tubular neighborhoods, or actually away from the union of, let me say, S is the complete singular set of the vector field. So away from S, the vector field is non-vanishing. So it gives you a representative of the Chern class, which actually lives in H2n of x relative to x minus S. Okay? And if you take the inclusion from x into here, you have a map into H2n of x, and that's the usual, what you get here is the usual Chern class. But this choice of vector field gives you a representative here. Okay? Now, this group, by well-known Alexander duality, is the same as H0 of S, which is, this is as many copies of the integers as connected components you have. Okay? And now this, you can include it in H0 of x. So the class you get here is a sum of classes here, here, here. So for each connected component, you have an integer. You look at those, you include them here, and then Poincaré duality tells you that this is isomorphic to this. And then the theorem is that the top Chern class is the sum of these contributions at the singular set. Okay? So for each component of the singular set, we are localizing the top Chern class. Okay? And those localizations give you a homology class here, and its dual here is the Euler characteristic. In particular, if all components are points, this is the Poincaré-Hopf theorem, but it's much more general. Just we only need that the connector, the singular set be compact. And then this is the idea of the bound-Bott residues. Under certain appropriate conditions, cohomology classes, certain cohomology classes can be localized at the connected components of the singular set of the foliation. Okay? So now if we have a singular foliation, we go back to the original case, and no, this is already. Okay. This is what I just said. This is just, I explained already this. Now, given a holomorphic singular foliation, we want to localize certain cohomology classes in the philosophy of bound-Bott. So we look at the singular set of the foliation, and we consider for each connected component, we look at a neighborhood, regular neighborhood of the component. Then the vanishing theorem can be refined to show that if you have a cohomology class of dimension 2D, where D is greater, here this should be n minus k. That's a mistake because I first took a foliation of dimension k, and then it became codimension k, and then it mixed up. But here, if you take a polynomial of degree more than the codimension, which is a polynomial in the Chern classes of the normal sheaf, then this polynomial represents naturally an element in this homology group. Okay? And then if we take all these homology groups, we include them in the homology of X, and we go back to the cohomology, we recover the original class. That's the theorem. So we have a compact complex manifold, we have a polynomial of high degree, high enough degree. Then for each connected component, we have a residue class, a localization of this class and this component using the foliation. And such that if we take these classes and we look at their image, we take the inclusion to homology followed by Poincaré duality, what we get is the original cohomology class. That's the theorem. Okay? Now, why all of this? Because we are going to use for the theorem a very specific cohomology class, which is localizable in this way. So let me give an outline of the proof. So we have a k-dimensional holomorphic foliation. We have the normal bundle. So the codimension is n minus k. So we are above the codimension. Okay? So the bound-bound theory applies to this cohomology class. We consider the connected components of the singular set, which are of dimension k minus 1. So notice that this naturally lives in H 2n minus 2k minus 2, the chair class. And by Alexander duality, since the dimension, the manifold has complex dimension n, this is the same isomorphic to H 2k minus 2. Okay? So this class, it has residues in this homology group. Okay, now the ampleness condition and quite a careful work tell us that, I mean, the magic thing is, so the bound theorem tells you that this cohomology class, let me just denote it by phi. Phi is C1 of the normal bundle to this power n minus k plus 1. Should be plus 1, yeah, plus 2. Tell us that this is the sum of the residues over the connected components of the singular set. Okay? That's the theorem. Then what we do is showing that ampleness and blah, blah, blah gives you that each of these residues equals the total. Okay? And they cannot be zero for ampleness. So if this is a sum of things and each one of those is equal to the total, then there can be only one summand. That means there's only one connected component. Okay? So that's the philosophy we follow. The rest is proving that it is true. Okay? Well, so we use this. I know that this gives you you make on digestion, but it is very simple. All is elementary algebraic topology. If you have x minus s, if you have this cohomology group, then the inclusions give you morphisms into, for each connected component, you have a tubular neighborhood of the singular, of the connected component of the singular set. You have this morphism, then you have this map into cohomology with compact support. Here, again, this is induced by inclusion. Here you have Poincaré duality and its inverse. Now for each of these, you have Alexander duality and its inverse. These are induced by inclusions. There, each of these is, you have Poincaré isomorphism and its inverse, inclusions, Poincaré morphism. So everything is very elementary. It's many arrows, but it's very elementary. And we are going to use it very much because our residues live here by definition. Okay? But we can push them here, then here, and then here. And we want to work with them here. Okay? So we have the chain class of the normal bundle. That's always the same as the chain class of its determinant bundle. And what I said, the residues are classes here in this homology group. And then using the previous diagram, we can bring them up to here. And the original cohomology class we had is the sum of all these residues. That's what we are saying here. Then, okay, and then the ampleness condition tells you that this set, tells you that this class cannot be zero. And if this cannot be zero, this cannot be empty. Okay? Now, we consider the pairwise disjoint to regular neighborhoods. And then from the above diagram, just for following arrows and blah, 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 we get that if we take the foliation and we restrict it to each open neighborhood, and we look at the residue class there, it is the same as taking the original residue of a bound and then pushing it to the corresponding homology class using the inclusion. And then that's the same as this. So it's just playing with inclusions. So now each CI is a connected component of the singular set, but it may or may not be irreducible. We split it as union of irreducible components. Those are these things. Okay? So each of these, we write it as union of irreducible components. Then the homology in dimension k minus 1 for each of these is isomorphic to the integers, or to C, sorry, to C. Okay? Then using that, we can prove that in this cohomology group, we get an equality like this. These residues, the sum of these, can be expressed like this for some complex numbers. Okay? Which numbers we don't know, but for some numbers, this sum of residues, which is the chain class of the determinant bundle, is expressible like this. We are going to keep that formula. Sorry. Yeah. Okay, then now, by ampleness of the normal bundle of the determinant, we know that we have an embedding of X in the projective space. That's somehow the definition of ampleness. And for some large enough N. So the normal bundle can be expressed as the tautological bundle of Pn restricted to X to some power. Okay? Then we have this equality, where this is the homology class represented by a generic hyperplane. Okay? Okay, then we just play with these numbers. We use that the foliation is of dimension more than 1, you know this is false, and we get this equality. It's not obvious, but I mean, you just have to do carefully all the computations and so on, and you get that. Okay, so now we put this in the memory for a moment, and now go to projective space. We take n minus k plus 1 generic hyperplanes, and we look at the intersection. So we have a complete intersection. Okay? And we recall that the H we have here, this H is the generator, well, is the C1 of the tautological bundle over X. Okay? Then you have these numbers, intersection numbers, which are positive, and we call them like this. We give them a name. Now, you look at Poincaré homomorphism in inverse, and that gives you that the cap product of each of these guys with this to the power k minus 1 equals this, but essentially by definition, equals this. And well, essentially, each of these PIs can be defined as before by generic hyperplane sections using this. So we have this equality, and then we put them together, and we get that these numbers are this sum. So this is, and then we are essentially done. We put together the total chain class is this by Van Vogt, and by the previous computations it is this. And then taking coproduct with h to the k minus 1, and using this, that this is this, we get that this equals this, and this equals this sum. And this is, here is not correctly expressed, here is this sum. We have this, but counted one time for each connected component. But this equals this. So the number of connected components has to be 1. Okay, that's, thank you. I don't know if I was too fast.
Thank you very much for your talk. Are there any questions? Maybe I have one, but just for personal curiosity. Do you know if there are some similar formulas as the bottom index for principal bundles? Because this is for vector bundles.
Yes, for vector bundles.
Do you know if there exists something similar for principal bundles?
I have never seen,
Okay.
I don't know, but I have never seen. No, good question, but I don't know.
Thank you. There are questions?
I have, say, two questions. One, I didn't understand, so you wrote this formula that the sum of Van Vogt residues is equal to this Chern class.
Yeah.
This I can understand, but somehow philosophically, what is the reason that each one of them is equal to the Chern class?
That's
It's not, you cannot explain it.
I mean, maybe someone more intelligent can explain it. In my case, I would apply something I learned from Gomez-Mont long ago, that sometimes the pencil is more intelligent than you. So you prove something, and then maybe you can understand it, but you prove it. So we make all these computations, and one finds this.
And maybe another question is there some counterpart, a real counterpart?
I know almost nothing, but yes, the original paper by Bott had two parts. One for holomorphic foliation, and the other for, I think, if I'm not mistaken, Riemannian foliations involving Pontryagin classes. I haven't seen, but there must be, no, I mean, I haven't studied, but I know there exists the theory of residues in that setting. I have never seen it, but I know it exists.
Are there more questions? No? If there are no more questions, let's thank the speaker again.
Thank you. Thank you.